Welcome friends. In this video we are discussing a special group that is integers modulo n. But before discussing this topic we need to brush off the ideas of relations and equivalence class. So we will briefly revisit the concepts and the detailed video on this topic will be in the description box. Okay, first of all, a relation from a set S to a set T is a subset of S cross T. So S cross T will be a ordered pair x comma y such that x belongs to S and y belongs to T, correct? And we will denote a relation, then we will say that x is y related. So this is the notation that we shall follow. Now in specific, if S equals to T, then the relation is said to be on a set S. Okay, now the second definition is that a relation on a set S is said to be equivalence relation if this relation is reflexive. Suppose this is a relation on the set S, then this relation is said to be reflexive if x is related to x for all x belongs to S. It is called symmetric relation if x related to y implies y is related to x for all xy belongs to S. And it is called transitive relation if x related y and y related z implies x is related to z, where x, y, z belongs to S. And finally we are defining the equivalence class. Suppose the relation is the congruent relation or any relation denoting by this symbol. If this is an equivalence relation on a set S and x belongs to S, then the set E suffix S is the set of all y such that this is small x, y is related to x. So we are clubbing all the elements that are related to the particular element x belongs to S, and we will denote this set by E suffix S, and it is called the equivalence class of x, and this is also denoted by this or this. So these are the preliminary definitions required to understand equivalence relation. Now the second definition is about the partition. So basically, pictorially, if we want to understand what is partition, suppose we have a set S, then the sets A1, A2, A3, so on are said to be the partition of the set S if all these AIs are pairwise disjoint, number one, and number two, their union is the set S, that is union of all AI over I is the set S. So this is pretty much preliminary definition of a partition of a set. Now equivalence relation and partition of a set are fairly connected things. Basically we can arrive to a partition on a set S from a equivalence relation and we can define equivalence relation if we have a partition of a set. So suppose we have a set S. Firstly, what we want to achieve the partition from equivalence relation. Equivalence relation to partition. So suppose first of all S is a non-empty set, and suppose this is a relation on the set S. Then basically the equivalence classes defines a partition on the set S. That is, theoretically, if we want to say, for any xy belongs to S, the associated equivalence classes Ex and Uy are either equal or disjoint. Second is, for any x belongs to the set S, there exists an equivalence class Ex of x that contains x. So either Ex equals to Uy or intersection Uy is phi. So we can achieve to a partition. Basically, from this result we can say the set of disjoint equivalent classes forms a partitions of the set S. Secondly, if we want to achieve the equivalence relation from a partition, from a partition to a equivalence relation, so suppose we have a non-empty set S and say A1, A2, A3, An is a partition of S. Then we can define a relation X is Y related if and only if X and Y belongs to a same set AI from the partition. This relation is a equivalence relation So in order to get the complete proof of these results, check out the link in the description. Now finally we are in a position to discuss the group Z quotient NZ, that is the integers modulo